Hi there, Mr. Sutton here with the BC Calculus 7-8 Extra Practice Number 3 solutions on interval of convergence. For this problem, we're trying to find the radius of convergence. Since this is not quite an exponential function, we're going to have to use the ratio test. So I've got the limit as n approaches infinity of the n plus 1th version of this. So that's going to be radical n plus 1 times x to the n plus 1 over 3 to the n plus 1. And by the way, all of this is inside one big absolute value here. So we have n plus 1th version of that over the nth version of this, which is just what you see there. So we'll put that down in our denominator. And now same change flip. We've got radical n plus 1 times x to the n plus 1 times 3 to the n in the numerator. And in the denominator, we have 3 to the n plus 1, radical n, and x to the n. These 3's can cancel, leaving me with just a 3 to the 1 power in the denominator. And these x's can also cancel exponentially, leaving me with just an x upstairs. So when the dust settles, in the numerator, I still have an x and a radical n plus 1. In the denominator, I just have a 3 and a radical n. As n approaches infinity, we can ignore this plus 1 in here. So we really just have x radical n over 3 radical n. Radical n's can cancel, leaving us without the limit now as with just x over 3 in the absolute value. For the series to converge, this must be less than 1. And to get my radius of convergence, I need to have a coefficient of 1 on the x. I have to have x minus a less than 1 form. So let me multiply everything by 3 to get my x coefficient to be just 1. So that's absolute value of x less than 3. And then whatever's over here is going to be the radius of convergence, which just happens to be 3 in this case. To find the radius of convergence on this series, we first hope that it's a geometric series, which it isn't. So that means we have to use the ratio test. So we'll do the limit as n approaches infinity of the absolute value of, and now big fraction. Up top we have the n plus 1th version of this. On the bottom we have the nth version of this. So n plus 1th version of this, that's going to be n plus 1 times 2x minus 5 to the n plus 1, all over n plus 1 plus 2, or n plus 3, however you want to write that. And downstairs we just have all of this stuff with no change, so just the nth version of that. Same change flip, multiply by the reciprocal to simplify our fraction. We have, let's see here, we have an n plus 2, we have an n plus 1, we have a 2x minus 5 to the n plus 1. All of that upstairs. And now downstairs, this is n plus 3. I'm going to simplify that too. And we also have n and 2x minus 5 to the n. At this point, I can cancel out these 2x minus 5s at least a little bit. I'm still going to have a 2x minus 5 to the 1 upstairs, using my exponent rules to cancel those there. And nothing else changes. So upstairs, we have n plus 2, n plus 1, and 2x minus 5. Downstairs, we have n plus 3 and n. Again, that 2x minus 5 to the n got canceled out with the rest of those 2x minus 5s. So now, if I go to infinity with the n value, I can ignore the plus 2, the plus 1, and the plus 3 here, because those are all next to n. So as n grows to infinity, those become insignificant. So really, upstairs, I've got n squared times 2x minus 5. Downstairs, I've just got n squared. The n squareds cancel, so this constant 2x minus 5 is all that's left. So I've got absolute value of 2x minus 5. And for the series to converge, the absolute value of whatever's left over here has to be less than 1. To get the radius of convergence, I have to have basically 1x minus a form. So I need to get that coefficient next to the x to be a 1. The only way to do that is to divide everything here by 2. So I'm going to have absolute value of x minus 5 halves is going to be less than 1 half. And now that I've got just a 1 coefficient on the x, whatever's on the other side is my radius of convergence. So the ROC for this is just going to be 1 half. For this problem, I'm trying to find the radius of convergence for this series. Now, I happen to notice that this is a geometric series. The r value here is x plus 5. So to find the radius of convergence, we just need to take the r value, the absolute value of that, and set it less than 1. And then if we have this in x minus a form, whatever's on the other side is going to be our radius of convergence. Well, since the coefficient of x is already 1, that means the radius of convergence is just the one that we see over here. So ROC equals 1. To find the interval of convergence on this problem, we first check to see if we have a geometric series. We don't. This n factorial is not very exponential, so that means we're going to have to use the ratio test. So I'm going to take the limit as n approaches infinity of the absolute value of basically n plus 1th version of this over nth version of this. Since I've got the absolute value, I can ignore this negative in here, and for my n plus 1th term, I can just write x to the n plus 1 over n plus 1 factorial. Now for the nth term down here, I'm just going to write x to the n over n factorial. Again, the absolute value allows us to ignore this negative part. And now same change flip, I've got x to the n times n factorial in the numerator. In the denominator, I've got n plus 1 factorial and x to the n. X's are going to cancel here. So we've just got, this is, let's see, x to the n plus 1 minus n. So just x upstairs. No more x's downstairs. And these factorials also mostly cancel, leaving us with just n plus 1 in the denominator. So this ends up being just x over n plus 1, limit as n approaches infinity. Since only n is a variable here, that means only our denominator is growing as n approaches infinity. So this is all going to go to 0. Now, to converge, the nth ratio, which we just found here, has to be less than 1. Since 0 is always less than 1, and there's no more x's to plug in, since this is going to be a true statement no matter what we plug in for x, that means that our interval of convergence is going to be all x values, so we can write negative infinity less than x less than infinity. To find the interval of convergence on this, since this is not quite a geometric series, we have to use our ratio test. So we've got the limit as n approaches infinity of the absolute value of n plus 1th version of this over the nth term. So I can ignore this negative here because I'm using absolute value. So we basically have 2 to the n plus 1, and this is going to be n plus 1 plus 1, so n plus 2 if we want to simplify it. Here we've got x minus 1 to the n plus 1. And now downstairs we've got just 2 to the n plus 1, and x minus 1 to the n. And I don't have to do any same change flippery here. This is already ready to reduce. So these 2's can reduce to just a 2 in the numerator, and these x minus 1 terms can reduce to have just an x minus 1 in the numerator. So upstairs we have a 2, we have an n plus 2, we have an x minus 1. In the denominator, this 2 is gone, this x minus 1 is gone, there's just n plus 1 down there. So if I multiply all this out, we've got a 2n plus whatever, and we have this x minus 1 upstairs. Downstairs we have an n. Actually, as n approaches infinity, let's ignore these slower growing terms. So really then we just have 2n and an x minus 1 over an n. N's are going to cancel. We just have 2 x minus 1 inside the absolute value. And to converge, this nth ratio that we just found here has to be less than 1. So we're going to set the absolute value of that less than 1 and solve for x now. I can start by dividing everything by 2, so that's going to be a 1/2. And I'm just going to rewrite that with the double inequalities. So I'm going to write negative 1/2 less than x minus 1 less than positive 1/2. Adding 1 to all three sides here, we've got, and we're basically adding 2 over 2. So this is going to be 1 over 2 less than x less than 3 over 2. Or is it? So now we have to test out the endpoints because we just used the ratio test, and we never really know whether the endpoints are included or not if we've used the ratio test unless we test them specifically. So let's start with 1/2. Let's say x equals exactly 1/2. Going back to our original series, if I plug in 1/2 for x, this now becomes negative 1/2 to the n. I can combine this negative 2 to the n and the negative 1/2 to the n. Negative 2 times negative 1/2 is just 1. So we just have 1 to the n times n plus 1, which is just going to be n plus 1. Now this does look a little suspicious. Let's use the nth term test on this thing. So limit as n approaches infinity of n plus 1 is going to be just infinity. Since that's not 0, we're going to diverge on this endpoint by the nth term test. So definitely not including 1/2 in the interval of convergence. Now we'll try out if x equals 3/2. So plugging 3/2 in for x up here, 3/2 minus 1 is 1/2. So we have a 1/2 times a negative 2, all of that to the n. That's negative 1 to the n times the n plus 1 that's still left over there. And if we try the nth term test on this, well, you're basically going to end up with either positive or negative infinity, depending on what your n value is, if you go on long enough. Either way, that's not going to come out to 0. So this one also diverges by the nth term test. And our final interval of convergence is just 1/2 less than x less than 3/2. For finding the interval of convergence on this series, it helps if you rewrite this a little bit in the beginning. Since both the numerator and denominator are both essentially exponential functions with an n in the exponent, I can rewrite this as x plus 1 squared over 9, all of that raised to the nth power. So basically undistributing this n from the numerator and denominator. Once I've done that, I see that I do have a geometric series with an r value of x plus 1 squared over 9. So to find the interval of convergence, I just have to take the absolute value of this and set it less than 1 and solve for x, and that'll be it. So doing that, absolute value of that less than 1, I have to start by multiplying both sides by 9. So I have absolute value x plus 1 squared less than 9, and then square rooting both sides. Now I have absolute value of x plus 1 less than 3. And rewriting this without the absolute value, I can write negative 3 less than x plus 1 less than positive 3. Subtracting 1 everywhere, we've got negative 4 less than x less than 2. And since there's no ambiguity at the endpoints for a geometric series, unlike using the ratio test, that means that this is the final interval of convergence. For this one, I'm trying to find the interval of convergence for this series. Now, you might notice that both the numerator and the denominator are exponential terms. That means this is going to be a geometric series. The r value here is just x minus 4 over 3, since that's essentially what we're multiplying by each time. So to find the interval of convergence, I just take the absolute value of r and set that less than 1 and solve for x. So first step here, let's multiply both sides by 3. So we have absolute value x minus 4 less than 3. And then rewriting that without the absolute value, I have negative 3 less than x minus 4 less than positive 3. Subtract, actually adding 4 to all three sides here, we've got 1 less than x less than 7. And since this is a geometric series, we never include the endpoints in the interval of convergence, so this one is done. To find the interval of convergence for this non-geometric series, we're going to have to use the ratio test. So I've got limit as n approaches infinity of n plus 1th version of this over nth term, all inside an absolute value. So we've got then n plus 2 factorial times x to the n plus 1. That's the n plus 1th version of that, all over n plus 1 factorial x to the n. Simplifying this a bit, this n plus 2 factorial is essentially n plus 2 times n plus 1 factorial. So if I cancel it with the n plus 1 factorial down here, all that's left is an n plus 2. And with these exponential terms, just subtracting the exponents, we're basically canceling out everything except an x to the first power upstairs. So we end up with then n plus 2 and x and nothing else. So as n approaches infinity for this whole thing grows without bound to infinity. Now, in order to converge, this nth ratio that we just found needed to be less than 1. Well, infinity is not less than 1. In fact, it's greater than 1. So that means that the interval of convergence is just going to be the center, which you always get for free. The center of this series is whatever zeroes out the x part of this, which is just going to be the x value 0, because that'll zero out everything, and then you're just adding a bunch of zeros together. So then our interval of convergence is just the x value 0. For this free response problem, we have a Taylor series about x equals 0, so basically a Maclaurin series, and we're told this converges for all x in the interval of convergence. Nth derivative at x equals 0 is given by this formula here, but note that this formula only works for n greater than or equal to 2. If you try plugging in 1, you get a 0 in the denominator, and if you try plugging in 0, well, I'm sure nothing good happens there either. So they do also tell us, though, that the graph of f has a horizontal tangent line at x equals 0 and f of 0 is 6. So our first task, figure out if we have a relative max, min, or neither at x equals 0. Since we only have information about this function at exactly x equals 0, we can't use any kind of sign analysis around critical values to help us out. We're going to have to use the second derivative test. So my first derivative, to find this, it's worth noting that our graph had a horizontal tangent line at x equals 0. This means then that f prime of 0, the slope at 0 of the original graph, must be 0. So we've established we have a critical value there at least. Now we have to know what the second derivative at 0 is. Well, for that we have to use this formula up here. Since we're taking the second derivative at 0, we're basically plugging n, or 2 in for n, for all these n values. So we're going to have negative 1 to the 2 plus 1 times 2 plus 1 factorial. That's in the numerator. Downstairs we have 5 to the second times 2 minus 1 squared. Cleaning this up a little bit, this is going to be, let's see, a negative 1. This is a 3 factorial, which is really 6. So we have negative 6 over 25 times 1, so a negative 6 25ths. Now the important piece of this is that this whole thing is negative. Since our second derivative is negative and the first derivative is 0, we've got basically the extrema on a concave down curve. We're at the top of the frown, which means that f has a relative max at x equals 0. For this part of the problem, we want a third degree Taylor polynomial for f about x equals 0. To write this using our Taylor formula, we're going to have to know the function value and the first 3 derivatives at x equals 0. So they told us f of 0 was 6. F prime of 0 we already found was 0 because we had a horizontal tangent line. So that taught us about f prime. F double prime of 0 we saw in part A was negative 6 over 25. Feel free to go back and review that. We just plugged 2 into this formula basically. Now to find f triple prime of 0, we have to plug 3 in for n in this formula. So that's negative 1 to the 3 plus 1 over 3 plus 1 factorial, all over 5 to the third and 3 minus 1 squared. Cleaning this up a little bit, this is negative 1 to an even power, so that's just 1 and we can ignore it. We have a 4 factorial upstairs then. Down here we have, let's see here, this is going to be 3 minus 1 is 2, squaring that gives us a 4. 5 cubed is 125. We can actually, 4 factorial is really 4 times 3 factorial. So we can cancel out the 4 from 4 factorial, and we just have 3 factorial, which is just 6 in the numerator, and 125 in the denominator. So a whole bunch of needless simplifying, but we did it. So we have 6 over 125 then for f triple prime of 0. Now to write out my actual Taylor polynomial, I'm going to have f of 0, which was 6, plus f prime of 0 times x, since this is about 0, it's just a Maclaurin series. We don't have to write x minus 0. But we saw that f prime of 0 was 0, so I'm not going to write any linear term. So let me just move on to the quadratic term then. We have f double prime of 0 times x squared over 2 factorial. So this is going to be negative 6 x squared over 25 times 2. And then we're going to have, let's see, we're going to have f triple prime of 0 times x cubed over 3 factorial. So that's going to be 6x cubed, and this is going to be positive now, 6x cubed over 125 times 3 factorial. Don't forget the 2 and the 3 factorial were from the Maclaurin formula themselves, not part of the actual derivatives that we found here. So if you wanted to clean this up a bit, we could rewrite this as 6 minus, and let's see here, this is 6 divided by 2, so we could write that as 3x squared over 25, and for this one, 6 and 3 factorial are really the same thing, so this is just going to be x cubed over 125, and there we are. For this part, they want the radius of convergence for the Taylor series of f about 0. All right, well, let's first come up with the nth term, because to find the radius of convergence, we usually have to do n plus 1th term over nth term, at least if it's not a geometric, and we don't even know if this is going to be geometric when all is said and done. So let's get the nth term. That's going to be the nth derivative at 0 times x to the n all over n factorial. So that's kind of a general expression for the nth term of a Maclaurin series. And now we actually have a formula for the nth derivative. It's this crazy thing right here. So we'll just replace nth derivative of 0 with this. So time to clean this up a little bit. This negative 1 to the n plus 1, we're not really going to worry about that a whole lot. N plus 1 factorial and n factorial, those can certainly cancel a little bit. That just leaves me with an n plus 1 upstairs and no factorial at all downstairs or anywhere else. So we have n plus 1, we have an x to the n, we still have a 5 to the n and an n minus 1 squared. And that's about as good as this is going to get. So taking a look at this, is this geometric? It is not. This n minus 1 squared is messing us up. So is this n plus 1 for that matter. So we're going to have to use the ratio test then to find the radius of convergence. So I'm going to take the limit as n approaches infinity of the absolute value of n plus 1th version of this divided by the nth term version of this. The nice thing is, since I'm doing absolute value, I can ignore this negative 1 to the exponent piece. But I am going to have the n plus 1th term. So that's going to be n plus 1 or n plus 2 times x to the n plus 1 all over 5 to the n plus 1. And this is going to be, well, I guess just n squared then if I'm doing n plus 1, n minus 1. So here is our n plus 1th term. Again, I just took all the n's from here and replaced them with n plus 1s. Now I'm going to be dividing that by the nth term. That's going to give me the nth ratio. So basically all of this stuff without the negative 1 plugged in pretty much verbatim. All right, time to do a little multiply by the reciprocal, same change flip business here. We've got n plus 2 times x to the n plus 1 times the denominator down here, 5 to the n minus 1 squared. So all that stuff. And now in the denominator, I've got 5 to the n plus 1 times n squared times n plus 1 times x to the n. So this is not really happiness right now, but we're going to cancel some things out. So we have, let's see, a 5 to the n and 5 to the n plus 1. Those can interact a bit, leaving me with just a 5 downstairs. Not much we can do for all these terms with the n's, but the x to the n plus 1 and the x to the n can cancel, leaving me with just x upstairs. So we have 5, that 5 is gone. We have just n minus 1 squared, n plus 2, and x in the numerator. And in the denominator, we have a 5, an n squared, an n plus 1, and that's it. So as n approaches infinity, we can forget about this negative 1 in here, this plus 2, and this plus 1. We've basically got n squared times n times x, so xn cubed in the numerator. In the denominator, we have basically 5n cubed. So the n cubeds are going to cancel, leaving us with just the absolute value of x over 5, or 1/5 x if you want to write it that way, either way. Now, to converge this series, the nth term has to be, the nth ratio, I should say, has to be less than 1. So setting this less than 1, to get the radius of convergence, we just make sure this x has a coefficient of 1. To get rid of this coefficient of 1/5, we just multiply both sides by 5. So I can write absolute value of x is less than 5. And then the radius of convergence is just this 5 that I see on the other side of my inequality. So ROC equals 5.